So, good morning, everyone, and welcome to this workshop, the first workshop organized in the framework of the BLAZETEC project. My name is Alejandro Bellucci from Istituto di Struttura della Materia, Consiglio Nazionale delle Ricerche of Italy. I'm the Exploitation and Innovation Manager of the project. I have the pleasure of being the moderator today. Just a few words on BLAZETEC. That is a European project focused on the development of next generation thermal batteries. That is an emerging technology with a great potential for efficient energy storage, decarbonization, and transition towards a more sustainable energy system. Few information to the audience. Today, the webinar will last about 1 hour. And during the presentation, please feel free to post your question in the chat. We will collect and discuss them during the roundtable and the Q&A session at the end of the webinar. We are also honored to have among the speakers, also Martin Schichtel, that is the CEO of Kraftblock. This is one of the global leaders in thermal energy storage solution, and his participation will certainly add valuable insight and perspective to the discussion within BLAZETEC framework. Of course, I would like to thank all the speakers and the participants of the panel for joining us today. I'm confident that this will be an inspiring on how innovation, research, collaboration within BLAZETEC can contribute to the future of clean energy storage. So, thank you for being with us, and let's begin with the first speaker. That is Daniele Trucchi from my same institution, Istituto di Struttura della Materia of CNR, who is the coordinator of BLAZETEC and who will present the objective and the main activities to be performed during the project. Daniele, the floor is yours.
Thank you, Alessandro. Thank you, Alessandro. Okay, I share the screen. Okay, can you see the presentation? Okay. Oh, is it okay, the streaming? Alessandro? Okay. Yeah, okay. Yes, I see. Sorry. Technically, yes. I'm the first one. So yes. So
now you remove, Daniele. You remove the presentation.
No.
Before we saw it, but now no.
Okay. Sorry.
Yes. That's perfect.
Okay. Now. Thank you. Let's start from a few words about BLAZETEC project. That is Horizon Europe project. BLAZETEC means breakthroughs in thermal batteries through zero-emission, high-temperature, static thermal to electric converters. Let's analyze what is a thermal battery. Thermal batteries can store energy with very high density. If thermal batteries are made of abundant and cheap materials, they can store extremely dense heat at a very low cost of stored energy, which can be orders of magnitude lower than electrochemical cells, for example. Thermal batteries can be charged by renewable energy, such as concentrated sunlight, or excess energy coming from wind or photovoltaic systems. The discharge of thermal batteries occurs by transmitting energy to the grid, and for this it is necessary to have efficient and compact converters. how to convert efficiently the stored energy. Historically, the technology used thermomechanical engines like turbines and Stirling engines. They work with hot fluids feeding the engines with the high thermal to electric conversion efficiency at high temperature. They allow cogeneration and energy storage. On the other hand, they are not compact systems. The efficiency depends on size. Especially for downscaling, they are so much limited. So the cost competitiveness of these systems depends on the scale. They get mechanical parts movement, so they experience degradation with operating time. On the other hand, solid-state converters, such as thermophotovoltaic, thermoelectric generators, and the fermionic energy converters, can operate at different temperatures depending on the specific technology. The efficiency does not generally depend on the size, so they are down and up scalable. They are static converters, so there is no need for maintenance, and they are connected with long operating times. On the other hand, they demonstrated over time a low thermal to electric conversion efficiency, lower than 10% for practical devices. In the consortium, we will work on solid-state converters. The consortium is composed by Consiglio Nazionale delle Ricerche with a group specialist in fermionic energy conversion, Universidad Politécnica de Madrid with a group specialist in thermophotovoltaics, and with CNR demonstrated the first hybridization of thermophotovoltaics with the fermionics. RGS Development is a high-tech small-medium enterprise specialized in production of energy solution based on thermoelectric generators. Ion Vac Process, another high-tech small-medium enterprise expert in vacuum and plasma technologies. The Cyprus Institute Research Center, expert in concentrated solar technologies, and giving the Proteas facility that will be a site for building the demonstrator. There are also associated partners, the Swiss Center for Microelectronic and Microtechnology in Neuchâtel, CSEM, ThermoPhoton, that is a startup focused on developing commercialized future thermal batteries. Let's discuss about the aims, the objectives of the BLAZETEC. We want to develop ultra-high temperature converters. This range of temperature ranges from 12 to 1600 degrees centigrade, starting from three legs, which are three technologies, thermoelectrics, fermionics, and thermophotovoltaics. The first objective of the project is to increase the efficiency of each technology and to increase also the output power density. After that, to hybridize them into fermionic thermoelectric generators and fermionic thermophotovoltaic generators with increasing efficiency and increasing output power density by taking the benefits of the hybridization. Finally, to introduce and integrate these converters into two demonstrators. One, sensible heat thermal battery working with a solar to heat to electricity cycle, and the other demonstrator is latent heat thermal batteries based on electricity to heat to electricity cycle. The objectives can be resumed by this plot with conversion efficiency as a function of output power density. The first aim is to increase the efficiency of, for example, thermoelectric generators and fermionic energy converters, and also to increase the output power density of thermophotovoltaic cells, and to hybridize them and to increase both efficiency and output power density. Thank you for the attention. I leave the floor to the colleagues which will give details about the technology.
Thank you, Daniele, for the presentation. I would like to repeat that we can collect questions and we'll discuss them at the end of the webinar. Now it's time for the presentation of Professor Alejandro Datas from Universidad Politécnica de Madrid in Spain, who is the work package leader of work package 1 and 4 in the project. And today he will give us an overview about the importance of thermal energy storage and the potential of solid-state converters in thermal batteries. So Alejandro, please, you can share the screen.
Okay, thank you, Alejandro. I already shared it. Can you confirm that is okay?
Yes.
Okay.
Yes.
Fantastic. Thank you. Thank you very much for the introduction, for organizing this workshop. And the intention of my talk is to provide a bit of context of the field of thermal batteries, which, well, is quite emerging, even though there are already quite a number of companies. But, well, I will try to give a bit of context. So, so first of all, the main reason why we are doing this is because there is a huge heat demand in the European Union. For instance, 50% of the demand is for heat. And in this graph, you can see that this demand, there's different sectors for this demand could be divided in residential and industrial heat demand. And the temperature range is also quite wide. It's low temperature typically for residential, but also very high temperature heat demand in the industrial case. Like 11% of the global heat demand is for high temperature. And so there is a challenge to decarbonize this heat demand because the other main data is that most of it, more than 60% of this heat demand is satisfied by burning fossil fuels. So in this figure, you can see that, for instance, natural gas is the main contributor to the heat generation. So therefore, if we want to decarbonize and use renewables instead of these fossil fuels, in particular natural gas, we need to see what is going on with the price of natural gas. And this is the objective of this other plot, where we see the price of natural gas for non-household consumers and excluding also the taxes over the last decades in the European Union. So obviously, you see that there is a peak there in the price in 2022 to 2023 due to the war in Ukraine. And this has triggered all the technologies that we are developing, even that these technologies were developed before that. This has accelerated all the process. And if we compare it with this, and I think this is quite important representation, with the levelized cost of electricity for solar and wind, we see that we're indeed living a quite historical event, which is that solar and wind electricity is now cheaper than natural gas, and at least in the European Union. And this is quite unique, and as you can understand, is triggering a big interest on using electricity instead of natural gas to produce the heat. And this is about the cost, but the interest is even higher if we look at the price, because in the markets, at the end, the price, as you probably know, goes to zero when there is a surplus of electricity. This is a real case in Spain in June this year, where during the solar hours, the price went completely to zero. And obviously, industries were looking forward to use this very cheap energy instead of burning natural gas. And the problem is that renewables, in particular solar, is intermittent. So you cannot produce all your heat using this electricity. And this is where it comes the concept of a thermal battery. Okay, a thermal battery in a first approximation can be assumed to be a system that basically converts electricity into heat, stores it very well efficiently and at very low cost in particular, okay, because you can use cheap materials to store the heat. And then with a heat exchanger, you can produce the heat to the demand. Okay, this is the simplest form of a thermal battery. Then what happens is that once you have the heat, you have the energy stored, there is a very particular interesting concept where you can convert the heat back to electricity. And there we have the power to heat to power concept, or sometimes also named Carnot batteries. And then we can also supply the electricity demand with the same thermal battery, just adding there the heat to power conversion. But if we further elaborate a bit the concept, we know that we can generate the heat not only using electricity, but using, for instance, sunlight through concentration, or even the waste heat in industry. So there are other inputs to the system. So this illustrates all the possibilities of thermal batteries regarding input energy and output energy. Okay, so and currently there are companies and research institutions that are pushing these concepts, and I want to provide the following kind of graph that classifies these companies. This is from Future Clean Tech Architects, that they classify this company according to the temperature of storage and the purpose of the system, whether it's for producing heat, electricity, or cogeneration in the intersection of the two. Okay, so you see that there are companies in all these applications, okay, and temperature ranges. If we look at the energy input, there are also a way of classifying this, and please take into account this is not an exhaustive list, and of course it might not be accurate, because maybe if you are one of these companies, you may not identify yourself in one of these categories because you may have projects or things like that. I don't pretend to be very accurate in this, but at least to show that there is a broad range of types of companies targeting different energy inputs and energy outputs. And here also you have just visual representation examples of these companies, and so you can see that we are not just in the design phase, but we are actually building systems, and some companies are more developed than others and have already reached even commercial stage. But in this talk, I wanted to focus on a specific kind or subsector of these companies. And let me talk about these four. Okay, these are two based in the US and other two based in Spain. And the third common characteristic of these four companies are, first, that they use ultra high temperature storage materials. Okay, so they store energy at extreme high temperatures. And in this case, you can see that the energy density can be very, very high depending on the temperature you reach, and the delivered temperature. You can reach even 4,000 or 500 watts hour per liter, which is orders of magnitude greater than, for instance, molten salts or lithium-ion batteries. Okay, just as an example. But the real characteristic or common characteristic of these four companies is the energy conversion process. Okay, these four companies use thermophotovoltaic converters to produce electricity out of the stored heat. And this technology basically consists of a photovoltaic cell that is illuminated by the heat, the incandescent heat, and directly produce electricity. So it has solid state, no static, no moving parts, so on. And the main characteristic of these cells is that they can be extremely efficient because they can recycle outbound radiation. So wavelengths that are longer than the characteristic band gap of the cell can be reflected with a mirror in the back of the cell and recycled in the emitter. And if you look at the different efficiency numbers that have been attained in the last years, you see that several authors have surpassed already the 40%. Okay, and importantly, also in a wide temperature range. So typically you need very high temperatures, but you can get quite good efficiency almost at any temperature. And this is because of the high quality of the mirrors that have been developed in the last few years. If we zoom out a bit and see what this efficiency means in a context of heat engines, we see that thermophotovoltaics has already reached the efficiency levels of steam turbines or gas turbines. Okay, so this is quite a relevant milestone. Of course, it has been demonstrated at lower power levels, but still this is really important observation. Okay, this is why these companies are looking at this technology as a solid state, no moving parts, low maintenance technology to produce electricity. Okay, but of course, thermophotovoltaics is not the only solid state heat engine, as Daniele already explained. We could also use thermionic generators, which basically consist of direct emission of electrons and collection of them and to produce electricity, and also thermoelectric generators, which basically create a solid continuity between the hot side and the cold side, and produce a direct flow of electrons through the material. So the thing is that, to my knowledge, there are no thermal battery developments using these converters yet, or if they are still at very small scale. So I wanted to explain probably why is this happening, why we are not using this yet in business projects for storage. And I think this graph is quite interesting because it shows the two key metrics of solid-state energy conversion, which is efficiency and power density. Okay, so you see that thermophotovoltaics clearly stands because of the high efficiency, but it has not very high power density on the other hand. Okay, but on the other hand, you see that thermoelectrics, at least in laboratory scale, have demonstrated very high power density, but efficiency is low. Okay, and in the case of thermoelectrics, the thing is that it has not been quite developed in the last year because most of the activities were taking place in the past century, basically. So here we see that efficiency now is the key performance indicator for thermal batteries, because in principle you are using a very valuable energy that you want to convert efficiency. But this is not necessarily the case. Sometimes you can afford lower efficiencies if the input energy to the battery is very, very cheap, because in that case, cost is more relevant than efficiency. So this trade-off between cost and efficiency is basically connected to these trade-offs between efficiency and power density. And all these technologies, what they're trying to do is basically to go to this region where they combine high efficiency and high power density. And this is precisely what we are doing in BLAZETEC. In BLAZETEC, we are investigating these three technologies, trying to improve efficiency and power density through hybridization. Okay, the idea is to combine thermoelectrics with thermionics and thermophotovoltaics with thermionics as well, to produce two hybrid devices that can have higher efficiency and power density, and demonstrate them for the first time, I think, in thermal batteries context. So thank you very much, and that's all, and thanks to the BLAZETEC project, of course.
Thank you, Alejandro. Now it's time to present the companies within the BLAZETEC project, just to have an overview of some of the partners. And we can start with RGS. So, Ani, I think you can share the screen in order to present the work and the road towards a vision of industrialization for the project. So the floor is yours. You are mute. So.
Yes.
Okay. Now it's okay.
Perfect.
Thanks. The floor is yours.
Okay. So, good morning. I'm Aniruddha Ray. I lead the technology and development team at RGS Development. And in this presentation, I want to give you a little bit of a perspective of thermoelectric modules and applications, and our view of the model-based engineering approach that we partake in designing thermoelectric solutions for various applications. First, a brief history of the company. So we are a company of 20 people located in North Holland. We came out of the TNO, ECN, which was the energy center of the Netherlands in the north of the country. The three main expertise that we have is that we are trusted experts in thermoelectric conversion and space power systems. We are industrial leaders in silicon germanium alloys, which is a key alloy that has been used in many high temperature thermoelectric devices. We also have in-depth knowledge and capability for thermoelectric generator device design and manufacturing. So based on these three forms of expertise, we were selected for what we call our current flagship program, where we are collaborating with Aerojet Rocketdyne since 2018. So that's been almost 7 years, in order to recreate the GPHS RTG. So that's a general purpose heat source based radioisotope thermoelectric generator, which has been used in various deep space missions. For example, the Voyager, which you might have heard of, which left the solar system. And now we are recreating that in the next gen RTG. So here, the main objective for RGS has been to define and produce the silicon germanium alloy for this upcoming program. We are quite proud to say that over the last 4 years, we have gone through the entire qualification stage to make this thermoelectric material, and we were approved for that process this year in 2025. And this feeds into our entire model-based engineering approach, where we go through right from the materials all the way to the systems. So here you can see some of the snapshots of the various steps that we take. We make the materials, we design the architecture for a certain system. So for example, the system that Alejandro just introduced, a thermal battery, would be an example of such a system, where we can take in the heat flux densities, we can define what would be required for our module, and then we would simulate as well as produce prototypes for such an architecture. Then we do in assemblies, depending on how much power does the system require. So for example, here you can see one which is based off up to 15 of our smaller 100 by 40 modules to generate up to 100 plus watts of electricity. And then we also enable systems building. So here we are looking at testing these modules in various kind of environments, vacuum environments, as well as in inert gas operation. So we go through the entire chain, always with the perspective of the final application. So this model-based engineering solutions approach, we carry it out in 3 steps. We do first a pre-design of the tech solution. That's a thermoelectric generator solution over a period of 4 to 6 months, where we study the environment and we also simulate and define the best suited device for such an application. Thereafter, over a period of a year to 18 months, we do a detailed design and prototype production of the first prototypes of a thermoelectric generator. And we start testing and optimizing the TEG to operate in the final conditions. So once that step is complete, we go to the final one, where we establish a qualified production, because the materials have to be at a certain level. And then we start manufacturing the TEG solution based on that materials. Finally, we also support the system integration, because we have a perspective on the final application, because we can start simulating both the integrated device as well as the assembly in the final application. As an output of this, I can show you an example of our Thermogy products, the brand name that we use. Here you can see on the left side, one of our example modules, which is 100 millimeters by 40 millimeters in footprint and can generate up to 10 to 20 watts of electric. Here, the material that we use is silicon germanium, as I mentioned to you in the past. So that can survive up to 1000 degrees centigrade on the hot side, which makes it a good complementary for thermal batteries, where you would like to store energy at high temperatures as possible to enable that high energy density. Then we can also do different configuration. So here on the top right, you see more flat configurations for 100 by 200 watts of electricity, or even going up to 1 kilowatt, where you have cylindrical configurations of our modules. So this is what we propose, a TEG concept for various configurations based on device shape, surface, and architecture. In this presentation, I also wanted to show you a case study of this model-based engineering approach, where we work together with the University of Dayton in the US to integrate a thermoelectric generator around a GPHS block of nuclear fuel, which has been previously qualified in the US for space missions. So you can see it has to be rigorous, it has to be integrated, it can be done also in conductive coupling. And what we did was we take in 250 watts of thermal input to generate 10 watts of electric output. So we can work together quite closely with the system builder to get to a high specific power, which is a key performance indicator for these space systems. And then rapidly we do the prototyping and as well as the development from our side. Just a few takeaways from this. So we have this model-based engineering approach where we do multi-physics simulations to capture the coupled heat flow as well as the material transfer properties, and in order to generate electricity of the required amount across various operational temperatures. Here on the right side, you can see examples of the various products we generate and produce. So we have the Thermogy M, which is more of a mid-temperature module, while we also do key modules based on our silicon germanium materials, the T and the S, for different kind of configurations. We also make a cascade module, which is what we are developing within the BLAZETEC project to get to higher efficiencies by using materials and modules which are appropriate for the various temperature windows. So this model-based engineering approach and the workflow allows rapid iterations and also trade space explorations for the various applications. And we can do it with the limited prototyping. So with that, I would like to, thank you for your attention. And I'm looking forward to the questions at the end of the workshop seminar.
Thank you, Anu, for the kind presentation. Yes, you remember to the audience that they can make questions at the end of the webinar, where we will collect and discuss together. Next speaker is Alan Pino of Thermophoton. We represent the second company of the BLAZETEC consortium that we would like to present today, and he will show the core business of the company and how its presence is important in the BLAZETEC project. So Alan, I see your screen and the floor is yours.
Good morning to everyone. Thank you, Alejandro, for the introduction, and to the BLAZETEC project for the invitation to participate in this workshop. I will show you how our thermophotovoltaic battery turns cheap electricity into on-demand heat and power. So starting with Thermophoton, we are a deep tech spin-off of the Technical University of Madrid, Universidad Politécnica de Madrid. We are currently 12 people, 7 of them founders, and also 5 full-time engineers, combining business, thermal engineering, and thermophotovoltaics. It was founded in 2021, and we have been active since then. To start talking about our solution, we will start with the problem, and it's basically that about half of the total global energy consumption is in the form of heat, about 20% of electricity, and so about 70% of the energy consumed is exactly what our solution can provide. And if we see also this curve, this is the electric price of a wholesale market in Spain. And we already have seen it, but we can have on the same day very cheap prices, even negative one, and very expensive, usually before and after the solar time. So it makes a lot of sense to store this electricity when it's cheap and then use it when it's expensive. And this is the basic on our technology. So we are developing the thermophotovoltaic battery, and we use this cheap electricity to heat up metal-based phase change materials, which are stored, and then we can supply electricity and heat to the end user on demand. To do this, we combine 3 key innovations, one of them being a very high density heat storage medium. So it's based on phase change materials. The second one, it's a safe and efficient indirect heat exchanger. We are working on that to supply high temperature heat. And the last one is the energy conversion. I will focus on this because of the topic of this workshop, and it's based on solid-state CPV modules. Yes, well, the introduction has already been made by Alejandro, but in simple words, the thermophotovoltaic cells are like solar cells, but instead of looking towards the sun, it is in front of a hot emitter. In this case, this is inside our battery, and it can convert these infrared photons into useful electric power. Main characteristic is that it's a solid state system, so it's completely a silent operation, no rotation parts, no moving parts like a turbine, and no working fluids. It can reach high efficiency conversion and power density when it works at high temperatures. And also other applications apart from thermal batteries can be recovery, heat waves recovery, or even concentration solar. In this regard, we are working on two fronts in our R&D department on TPV. So the first one is to scale from cells to modules. And here you can see one germanium cell of about 1 square centimeter and about 1 watt of power. And it can reach 12% efficiency. But this, we are using the cells to integrate them into useful modules that can already be used to get an electric output. So we have already moved from tens of watts to already 100 watts that they have been measured, and it is still increasing in terms of size. And the other branch, it's improving the performance. So exploring new materials and new designs of TPV cells, in this case are in-gas cells. We have reached already higher efficiencies, and if we compare with germanium cells, it's a huge improvement, and we are still working on that to have a more space efficient use of our system, and that will increase the total output. All this development happens mainly within the EIC transition project called ThermoVat. Here you can see our industrial and academic partners that are participating. And on the photo, there is our first thermophotovoltaic battery prototype. Currently, it's being tested at the UPM facilities here in Madrid. And it can store about 100 kilowatt hour and supply around 10 kilowatt of combined heat and power. It also has all the thermal system to supply domestic hot water, and it's include complete or extensive sensors, so we can characterize the behavior of the battery and then decide how to optimize both the TPV system and also the thermal subsystem. The next step could be go and install this technology into a real environment. So by early 2026, we have planned to install it in a sports center here in Madrid, together with our ESCO partner, Cerveo, who is also part of the project. And the battery will mainly supply electricity, but also domestic hot water, and for an equivalent of about 55 showers per day that will displace natural gas consumed by the sports center. And that would be all from my side. I want to thank you again for the invitation, your attention, and I'm looking forward for the questions.
Thank you very much, Alan. Now I have the pleasure of introducing Martin. I hope the pronunciation is correct. Schichtel.
Yeah, perfect.
Correct.
Okay. Correct.
That is the CEO of Kraftblock. That is one of the major players in thermal energy storage system, who kindly accepted to join the workshop. Few words to present Martin. Over the past 10 years, Martin has transformed the concept of affordable, flexible process heat into a company that now leads the thermal energy storage market. He has a background in material research, product development, and IP strategy. He holds a PhD in material science from the University of Saarland and worked in materials development and sales of energy efficiency solution for EV industry for 20 years before founding Kraftblock. Now you can share the screen, and the floor is yours. Thank you.
Wonderful. Thanks for the introduction, Alejandro. Great to be here and, let's say, present the Stone Age compared to what we have heard about BLAZETEC. And that's why we also said pioneering high temperature energy storages, right? Our ambition, first of all, was beneath offering a solution to the market to go for market education. Because if we talked 5 years ago to customers in the market talking about high temperature storage, most of them replied, well, cool, 120 degrees C hot water. We said, no, well, we're thinking more about 800, 1000, 1200 degrees or even more. So the market is still not fully aware of the options that thermal energy storage will give. That's why we started very low level, but there's obviously more to come. I will not go through this slide in detail. We already heard it twice. Heat is roughly 50% of the energy demand worldwide in process heat. Again, a huge portion of it. With Kraftblock, we basically focus more on the temperature range, storing the temperature, discharging the temperatures between 200 and 1300 degrees C, which already covers a quite good range of that heat segments in various industries. Briefly about the company. When we talk about Kraftblock, usually it is the company name, it's the product, and it's our team. So we all are Kraftblock somehow. We have been found, as you can see it, in 2014 already, in a quite early stage of the market, where just a few players were thinking about offering thermal storage solutions to decarbonize process heat. For us, it was a low-brainer to go over there. We've grown very much, 43 international, multinational team members. Meanwhile, a very small but a high-performing team, because we strongly back on a network approach. It means there are specialists for all types of the components we are using in the market. So why should we integrate it into the company itself, especially with the approach that we do have at the moment? Patents, of course, also very important. Then there is much more to come. 3 more families will be released this year, because we not only focus on the storage material or the storage itself, but on the whole storage system and definitely the processes, how to operate the storage. What is unique, what is different with us to many players in the market, we offer us what we call a storage platform. I will explain the principle in a slide later, which basically means you do have one standardized storage which you can connect to different charging or various discharging options, and create a huge degree of freedom to design the system itself. Sustainability, briefly, 2 angles. One, of course, is the customer, decarbonization and creating energy resilience. But for us, it's important as well. So we developed our own storage material, which is a ceramic-like storage material. It's fully inorganic, but we do not need any heat to cure it or to generate our ceramics. We do it at room temperature, just using a chemical process. So also there, saving a lot of energy and avoiding carbon dioxide emissions for this process. Modular and scalable, that's not a nice to have, that's a must have today. Because in most of the application you will see in the market, these are brownfield applications. So you need to adopt on the local footprint, you need to adopt on the process of the customer, which cannot be served by one standard solution. So we try to create a product standard for the customer and not try to customize or standardize our customer to our product. Durability, even before we released the first proof of concept, you will see it a little bit later, we fully tested our material and the storage itself for 15,000 cycles charging between 200 degrees C and 1,200 or 1,300 degrees C with nearly no degradation. And after the system passed this test, we started piloting and going for proof of concepts in the market. Excellent economics. We would need another 2, 3, 4 days workshop to discuss about that. But our ambition is, if we go for waste heat recovery, having payback times below 3 years. If we go for electrification, payback times definitely below 6 years. That's at the end what the market needs. Of course, we also have a very strong leadership and a funding team in the background to cover especially the commercialization of our project. Here's our journey from lab to industry. We started the company just with an idea in mind. It was pre-developed, yes. It was pre-calculated, yes, that's true, but not out of university. It was just a private pleasure that we had at the beginning. Then we developed our own storage material. We'll describe it a little bit later why it's that special and why it might offer a lot of options for future applications. As said, we tested it very strongly. In 2019, then we released our first proof of concept system to the market. Proof of concept is, in this case, a waste heat recovery unit in the ceramics industry, and that company is the top 3 company in grinding wheel production. So a lot of batch-driven furnaces recover the waste heat. Our storage operates as a kind of external regenerator, recuperator, circled it back to preheat the furnace during the next ramp up, which saves roughly 17% of gas, a lot of carbon dioxide, and makes the processes much more controlled with some additional value adds for the customer. 2020, this looks a little bit more strange, and the storage looks a bit different because that customer owns a fleet of 80 trucks. So we adopted the outer shell of the storage to the trucks itself as a Swift container. It's a mobile storage. So you charge it in one place, you put it on a truck, transport it somewhere else, and release the heat in a remote location, which is interesting for a kind of 2-point district heating system, flexible heating system, or even inside different production sites of large-scale customers. Mobile storage can be used. Unfortunately, then pandemics hit, but we used that time to combine our experience from the pilots before and the proof of concepts to define our standard storage, and went for the commercialization. So the first project, 2024, we started building it. Beginning of 2025, it was handed over to the customer. Also a waste heat recovery project in steel industry. We'll describe it a little bit later, with a wonderful performance. And the first electrification project, so replacing a 25 megawatt gas boiler against an rectified thermal storage, is now nearly completed in commissioning and will deliver first heat towards the end of this year to PepsiCo, the final customer, and of course the utility in between, delivering the green electron and doing the contracting services. What is the storage platform? What do I mean by that? What we did was to remove all the components to operate the thermal storage out of the storage and define interfaces to the charging system and to the discharging system. Means the storage in between is, we call it KISS, keep it simple and safe. It's a standardized module with quite already, meanwhile, 6 years operation experience behind. So a very good data set, which we then can combine with, let's say, a flue gas system for waste heat recovery, electrification of process heat using green electron. Also, even concentrated solar thermal heat can be used directly to charge our storage. Means basically we charge using a hot gas because we go to high temperature, and at the moment it's still more or less the cheapest heat transfer media that we can have. Discharging, of course, the opposite way. We use ambient air, go through the storage, and then to the discharging system, which might be a waste heat boiler, which might be an air thermal oil system, whatever it is. Important, and that's why I'm said we try to go for market education, and the system that we have in the market today is different than the one you will see in 10 years. But we need to create the system that can be understood from the customer, where you minimize the risk to a max. That's why we use only out-of-the-shelf equipment for charging and discharging. So tons of references, TRL9 equipment in the market. That's a perfect go in the combination. So yes, it's a first of its kind. Each time you do a new deployment, from hot air to thermal oil or electricity, power-to-power applications. But basically, we are backing very much on standard products. These are a couple of industries we are already working in, either deploy projects or start deploying or in the engineering phase. So quite a broad bandwidth from low temperature to high temperature industries, with typical processes you can find over there. And where I just marked it now with a green rectangle, those processes can easily be electrified to affordable cost to the customer. The orange one now just symbolize you can go for waste heat recovery in that case, because there is huge waste heat potential available worldwide in those industries, which would be the first step to tackle in before you fully skip the process and go for electrification. But you also can use both systems at the same time. Let's have a closer look to Kraftblock, to our storage device itself. Basically, it's that simple as shown here. We do have an outer shell, a static system. We do have inner insulation. We do have a very smart material inside, maybe also a smart stackering of the material. This can be pellets, this could be bricks, this could be a honeycomb system. Basically depends a little bit on the application and the capacity of the system. Our storage material is a development by ourselves. We have taken a look to chemical storages at that point in time. Well, too complex, too expensive. Phase change materials were also not in favor from us, because we said we want to have a storage that can operate in a whole broad temperature range rather than being focused on a special temperature segment. And also, of course, things like molten salt, right? Corrosion, system stability, degradation. Was quite early stage for those materials when we started. So we stayed with sensible storage materials. We are using mainly upcycled or recycled materials, for example, steel, slag, waste of bauxite production, waste of copper production, combine them with a special type of binder that we developed to our material, and then just put it into the storage device. Storage temperature, I said it at the beginning, maximum 1300 degrees C at the moment. The storage material itself could go way beyond 2000 degrees. So why do we limit ourselves to 1000 degrees? Again, keep it safe and simple. If we go higher than 1200, 1300 degrees C, the process architecture changes, the system setup changes, the integration to the customer changes, and there are just very few applications higher than that temperature level. So with this temperature cap, we could cover roughly 96% of the application in industries. That's why we're quite fine with that, especially thinking about commercialization and standardization. Let's have a closer look to the storage material to describe why it's that special. Our storage material, I explained it, is a combination of what we call capacity fillers and a very special binder. The capacity fillers, like steel slag, will mill them down smaller than 200 microns in a very specified grain size mixture to get maximum density of the core material itself. Then we mix it with our special binder. The special binder is a phosphate. What is the idea behind? Good heat capacity in sensible materials usually means worse heat conductivity. But if I want to follow a technical process very fast with low latency time, I need to have a very strong conductivity as well. As we now mix a strong conductivity with a phosphate-based binder with a good capacity, with the capacity fillers, we just can balance out what we prefer. Do we prefer more heat retention? We reduce the quantity of the binder. If we need a fast cycling system, we increase the binder slightly in order to charge much faster and discharge much faster. And that's basically seen in this microscopic view, right? We use those binders, which is the whitish lines in between the particles, to transport the heat deeply into the core of the material. So if you go for an IR photograph, unfortunately, I'm not allowed to publish it yet, but I think there will be a publication beginning of next year. If you charge the particle, you split it in the middle and take an IR photograph, you can see that the shell nearly is as hot as the core. And that's what we need if we want to have a very strong capacity and storage material use. Now, manufacturing and deployment is pretty simple. The storage modules are pre-manufactured. Here you can see two 20-foot containers welded together to a large-scale system, which is then put on top of a second container. Means in the inner segments between the containers, there are no walls, there are no ceilings, but we are basing them on the small modules. Then we fill it with the storage material, of course, do the interconnection to the full system. And that's basically it. Means also we try to reduce construction times on site, sorry. Basically, we also offer 3 basic modules, S, M, L, X. They might change in the future. We're focusing on smaller capacities at the moment because 80% of the requests that we have is below 150 megawatt hours. There are only a few going for gigawatt hour scale thermal energy storage at the moment. Net zero heat, what does it mean? And here we are close to the BLAZETEC system itself, using renewable electricity, convert it to heat, store the heat, and then deploy the heat to the different applications. We'll jump briefly over that slide because we heard that before, but important probably also for you, which costs are we talking about? And this is a graphic from McKinsey, which also was based on the benchmarking with our system, where we just compare the steam generation costs using a gas boiler, a hydrogen boiler, an electric boiler with a battery storage to balance out the price peaks, and the electric thermal storage, you can see that they are already quite competitive. Of course, it depends on the market, depends on the electricity price, the grid fees, and so on. But it's a very good approach to make thermal storage popular in most of industries. Here's a bit the same approach now for a market like Germany, and there is pretty much different. If I would go for electrification using an e-boiler, would be roughly at 100 euro per megawatt hour. Gas boiler, roughly 50 to 60 euro per megawatt hour. A electrified thermal energy storage hour system would already be 20% cheaper than the e-boiler, but still more expensive. And there are now a lot of people out there who do not want to hear that, but you need to go for economics, good economics for the customer. They do not want to wave the green decarbonization flag without having good economics. Means we do combine the gas-fired boiler with an electrified thermal system. Means roughly 5,000 operation hours electrified thermal storage, the remaining 3,700 operation hours the gas-fired system. So we end up in a steam generation price which is roughly 10-15% below the gas-fired price. So we combine economics and ecologic and climate impact. That's basically the project PepsiCo Anico. I will briefly hop over the site description. These were the first 2 units that we installed. Meanwhile, you cannot see anything at all because this is an integrated building, including transformers, thermal oil heating, thermal oil exchange, electrified thermal storage control system. So it's a mini thermal power plant in itself. We could go through it, but would take its time. Basically, these are example curves. On the bottom, there's the heat demand curve from our customer. In the top curve, you can see the electricity prices and especially the operations of the storage, when it charge, when it discharge. Green and red means direct electric heating, steam generation. Green means the storage is fully charged. It is able to operate. And that's basically the approach to the market that we see. Waste heat recovery, same setup. We just use a different charging system. Already explained this project in steel industry where we cover waste heat from the intercooler station. We, of course, need a back filter to clean the heat, take it to the storage and circle it back in a closed loop to the system again. The effect here, and the system is in operation since beginning of this year, payback time is less than 2 years, extremely important for the industry, and it increases the efficiency of the sinter plant by 2%, which is even a stronger value add. This is just a couple of pictures of the system. The storage device in the middle is the back filter and the whole infrastructure that needs to be integrated as well. Basically, I'm at the end with my talk. One remark, I said it at the beginning, we are Stone Age at the moment, but we are preparing the next step in the background because the storage will look pretty different in 10 years. And hopefully, and that's why I'm really looking forward to the results of projects like BLAZETEC, how power to power develops, how TPV and the thermoelectric conversion will develop in future and how it could be used. Thank you.
Thank you very much, Martin, for this very interesting industrial perspective of thermal energy storage systems. Now it's time for questions and a small round table. I will start with the questions that have been collected. The first question is for Daniele, but please also the other panelists can reply to it if necessary, or if they want to add something. It is what role do materials innovation and system integration play in improving the efficiency and lifetime of thermal batteries?
I think it is fundamental, the materials innovation, especially in BLAZETEC, with the nanostructuring the materials, with making the materials to be functional to a certain operation that the converter should have. In BLAZETEC, for example, we are developing some classes of materials that can be tailored and improved for increasing the conversion efficiency and also the durability of the radiated converters. For example, indium gallium arsenide for thermophotovoltaic cells, lanthanum hexaboride for fermionic energy converters, silicon germanium with accurate recipes for thermoelectrics. All of them are active materials which are processed with nanotechnology tools to develop future products which are cost competitive, and also they don't involve critical materials, or if critical materials are necessary, to reduce at maximum as possible the quantity of such materials. And but not only for active materials, but also this is done also for passive materials, because we are working at ultra high temperatures, and so also the casing materials and the interface materials are extremely important for the conversion efficiency of the overall converter. So it is, let's say, improvements which are at two levels, at material science level and engineering level, to develop the future efficient solid-state converters for high-temperature applications.
Okay, thank you, Daniele. The second question is for Alejandro. I think you already discussed about this, but the question is, how does BLAZETEC's approach differ from the other thermal storage technologies currently under development?
Mm-hmm. Yes, well, it's always good to insist on what is different and what is new. So basically, I will say that BLAZETEC is focused more on the energy conversion technologies. So the objective of the project is to realize the proof of concept of the validation of the technology in what is called relevant environment. In this case, it's a thermal battery, but the core of the project is in the energy conversion technology. So most of the innovation is related to that. It's true that we are doing electric and solar batteries, thermal batteries, and we are innovating also in that. But I will say most of the innovation is in the hybridization of these three solid-state heat engines, thermoelectrics, thermionics, and thermophotovoltaics, with two innovative hybrid concepts, which could potentially have better performance. These technologies, we hope to validate them at relevant scale already at the end of the project, and this will be the main outcome of the project. So I take the opportunity. I think later we will have the opportunity to discuss more, not just answering the question and discuss more freely, but I would like to also emphasize this heat to power conversion, which is not in the center now of all the commercial projects. I mean, most of the, as we have seen in Martin's presentation, most of the market is now focused on heat decarbonization. But I see the heat to power technologies as something more in the mid and long term that could be integrated in not only the batteries of companies already focused on that, but in all batteries. Okay, I think historical events matters on how the technologies are deployed, and in this case, heat decarbonization is clearly. I mean, I don't see competitors for thermal batteries in the field of heat decarbonization, or at least high temperature heat decarbonization. So I see a near future where we will have tons of batteries. I mean, many batteries installed with high temperature heat inside. So we will want to convert this heat back into electricity with technology like these ones. Okay. Comparing with other options, we will just need to add the electricity generation to these batteries. So we don't need to build an entire new asset to generate electricity. So I see that these projects on heat to power are trying to build a bit these technologies to be ready in 10 years, let's say, when this will be integrated in the batteries that will already exist at that moment. I see that we are kind of advanced in that potential future where we could have electricity generation in all these batteries. I would like to listen Martin's opinion about that, by the way.
Yes, I just add that one of the other question to Martin is how far are we to seeing large-scale commercialization of thermal batteries in Europe? That is something related, and which are the key factors that determine the scalability and the cost competitiveness of thermal storage systems? So it is quite correlated to this.
Yeah, it's very, very close to this, and basically I would agree to what Alejandro said. We faced when we started, right at the beginning, when you pop up with a new technology, a new system, everybody if you talk about commercialization, everybody will ask, well, did you already deploy it at 5 megawatt, at 20 megawatt, at 100 megawatt? What is the scale? How many cycles do you have? But we see that industries is losing that, let's call it risk anxiety that they did have in the past, because they need different options. They need new options now. But of course, they want to understand it and minimize the risk, right? So we will have a stepwise approach. And as I said, we are looking forward to power to power, because there are a lot of requests in the market for power to power or power combined heat and power discharge of the storage itself. But if you then go for a steam turbine, well, steam turbine usually is more expensive than the full storage system you deploy before. So economics, let's do a question mark. If you go for RC Stirling, well, different type of story that we do have over there. So I think a direct generation without any moving parts, any rotating parts, is a great approach, and that will definitely trigger power-to-power systems in the market that we see. How far are we from seeing large-scale commercialization? That's depending now on how we define large-scale, right? If you say, well, 100 megawatt hour, it's already large-scale compared to what have been deployed 4 years ago. Then we see it in the market, right? There are players like Brennmiller, not going for 100 megawatt hours, but I think they do have 5-6 systems in the market and in deployment up to 30-40 megawatt hours. We are now going for the 150 megawatt hour unit with 5 systems in the market, and a bit more to come in the background. Rondo, I think they do have 2 systems in the US at the moment, but announced 300 megawatt hour systems in Europe, in Germany, in Portugal, and in Denmark itself, funded by the EIB. So we can see that deployment of thermal storages is now gaining speed, right? So that pace that we have at the moment is much higher than in the past. But still, compared to gigawatt hour applications, these are small scaled. Fully true, but I think each project that is in the market is very important to show, well, there is a solution, dear market. Take it. You can easily scale it, because all the systems that we see are modular. So you can go from megawatt hour to gigawatt hour scale based on the experience, based on data you already have from the deployments. We do not, as Kraftblock, we actually do not see, let's say, a gigawatt hour storage, thermal energy storage coming up in the next 5 years, but we see more tendency to go to the 200, 300 megawatt hour range for different industries, to cover already a broad range for decarbonization of, let's say, 60% of the established heat processes that are used in the industry. And I think that's a stepwise market. And the more deployments you have, the more large-scale deployments, let's say between 100 and 300 megawatt hour you have, the more reliable technology gets. You come into economies of scale, make it more attractive to the market. It's a combination of different factors. One influence factor, of course, is also electricity price, right? Usually you need to benchmark an electrified thermal storage against gas price. Pretty hard to do. If you take a look to the generation costs, completely different story, right? But then you have taxes, you have grid fees, you have concessions on top of the electricity prices. And usually even that portion is higher than the gas price plus carbon dioxide and some other fees they need to pay. So we need to work on the electrical distribution in the broadest sense. If we have on-site PV, perfect go. If we can go for PPAs in the market in Spain, it's already great compared to gas in Norway. It's even electricity prices even more attractive than gas. So there are levers in the market to enable renewables to come in more and more and replace fossils. But there's a good portion of work to be done by the regulators.
I don't know if someone would like to add something. on this part. In the meantime, I will face other questions for general question. The first one is, are there any promising synergies between thermal and electrochemical storage technologies?
Maybe I start with it, and happy for the others to join in the second stage. I think as for now, yes, there are, because usually AFRR is one part of the revenue story for electrified thermal storages in the market, because with AFRR, so grid services, you generate a second revenue stream, which enables you to deliver heat to more attractive prices to the customer, right? So you need to balance out at the moment the disadvantage of the more expensive electricity in the market. And if you think then about frequency reserve or generation, then electrochemical battery could be a very good match. So thinking about 10 megawatt lithium battery, 100 megawatt hours thermal storage in the background, so you can go for arbitrage services. It could be also interesting in combination with TPV and other modules that are getting developed to go for power to power, because basically, and even there, I'm quite curious to hear the opinion of the panelists. You cannot ramp up a thermal storage within 10 seconds, right? With the battery system, you just turn the switch and you can charge and you can discharge. So it's much faster in interaction compared to thermal storage. Even if you integrate the heaters into the thermal storage, you are limited by the heat transfer from inside the storage material itself. Not necessarily the heat transfer from heater to the material, but the limited surface of the heating material and the heat transfer into the storage material. So even that ramp up from 0% from standstill to 100% would be like 1 minute, 2 minutes. With our system, with an externalized system, keeping the heaters on temperature, we can ramp up our storage within 30 to 60 seconds, which is already fast, but still too slow for typical AFR or other grid services, right? So the combination would make that solution, the combination of both options would make that solution attractive to a couple of customers in the market, which needs electricity, which needs heat at the same time, but generate a more reliable business case.
Yeah. Well, maybe you trigger a bit my imagination, but indeed, these solid state converters has this advantage of being faster. Maybe it's true that the problem here is how to switch on, switch off these technologies, because typically we need moving parts for doing that, and this takes time. Not the converter itself, but just switching on and off the converter. So I totally agree. We have analyzed this in other projects, the techno-economics of it, not just on the short time scale analysis, but more in the typical 1 hour resolution analysis and things like that. And we have combined thermal batteries with lithium-ion batteries and heat pumps, because these three technologies indeed are quite synergetic, and it's interesting to see how the integration, the optimal integration of the three depends on different parameters, like the coefficient of performance, the cost of the storage, the cost of the heat pump. There are many economic parameters that are interesting, and I mean, Alicia Lopez Ceballos is doing a PhD on this topic, and I may suggest to read her papers, and it's quite interesting to see how in most of the cases the optimal hybrid solution integrates both thermal batteries, heat pumps, and also lithium-ion batteries. So, and it's true that the economic benefit might be marginal in some cases, respect to the case where you don't integrate one of the technologies in some case. So, sensitivity analysis is always important in this kind of analysis of techno-economics. But I will say that thermal batteries are always part of the optimal solution, even with very efficient heat pumps and even with relatively low-cost lithium-ion batteries. So that's something that was surprising to us, because we were expecting that lithium-ion plus heat pumps could completely remove thermal batteries from the scenario, and that's not the case according to our simulation. So that's connecting to the question of synergies between electrochemical and thermal. Thermal storage goes to long duration cycles, and electrochemical to shorter duration, and looks to be a very good combination.
Alessandro, I see another question from the audience that would be interesting.
Yes.
to reply to. I read it from an industrial perspective. What sectors are likely to benefit most from the advances achieved within BLAZETEC due to the high temperature? And I would like to say that BLAZETEC uses high temperature as a tool to achieve a certain it's a certain efficiency for the converters. And for example, for the application of heat to power, all the sectors needing and with the excess electricity produced by renewables and so on, that needs to be stored can have benefits from this, because the high temperature is in this case an intermediate step for our technology. On the other hand, and I also ask the opinion, for example, from Marios Georgiou from Cyprus Institute, could revolutionize the concentrated solar power in terms that providing a conversion technology that is a solid state technology that can be applied to the receiver of concentrating systems can increase the cost competitiveness of smaller conversion considering sunlight plants, which limited the diffusion of, for example, of CSP in Europe and also in the world. Marios, what do you think about this possibility?
Well, first of all, thanks. I mean, indeed, higher temperatures obviously enable additional sectors. I mean, obviously, when we're talking about CSP, the typical temperatures that we operate is around 545, and then we want to scale down to basically go to the steam turbine. Now, having really high temperatures enables new getaways, solar fuels, for instance, which is something that can also be a really important aspect. And taking into consideration that now CSP, there is a dramatic increase from the Chinese aspect, and the cost of for CSP are dropping. New solutions and even higher temperatures are something that are now really emerging. So we are in a new era, because obviously CSP is not a new technology. It's something that has been there for decades. But in Europe, it has been fading out until recently. However, based on the new developments that are taking place in China, now this is getting lots of attention also in Europe. So this creates a good momentum and a good opportunity for new technologies and new concepts, like the ones we're discussing here and exploring through BLAZETEC, to actually enable higher temperatures, new getaways, new technologies, and at the very end to basically check how we can efficiently convert these high temperatures into storage, into heat, into power. So, and then, Daniel, I hope that this is basically what you're hoping to get. If not, happy to elaborate further.
Thank you, Marios.
I would like to add to that about CSP technology, mainly the central tower receivers. And I think that changing, because well, apart from the storage, they require a power cycle to transform into electricity. And the large projects that have been constructed in the past years in the US, in Chile, and other places, they have failed in the known technology that is already the power block, but also combining molten salts and all that. So since the heliostat and concentrating all the solar in a very specific area can turn into direct electricity with the solution of the BLAZETEC project, I think there could be a good achievement, like replacing the big system. And also, since it's modular, you don't need to create a 100 megawatt central receiver just to try if it's working. So from my point of view, that could be also an outcome.
So, Alan, if I just add on what you're saying, I mean, it's really now, I mean, the good thing is that we're no longer talking about these huge plants with really high towers, I mean, 220 meters, but exploring multi-towers solutions, which is smaller towers, and also having the ability to have modular heliostats being able to point in parallel. It's something that also adds on what you're saying. I mean, having flexibility to also get rid of traditional methods like the ones that we're using in the research infrastructures with molten salt, for instance, and avoiding freezing and all the parameters, circulation, losses all around the lines and all these. If you have the option to actually use this energy and being able to convert directly into electricity and having the add-on of storage, this is something that is really quite important. And therefore, yeah, I mean, your point is quite correct that this is a good opportunity, and not having also to go to the traditional models, but exploring new advanced models that seem to also getting more attention because they also need lower space, less requirements, less impact. So everything plays its role.
Yeah, well, exactly. I mean, maybe downscaling, because from the economies of the scale, having a huge power block will reduce a lot of cost. So yeah, having a smaller system, in this case, if the technology allows modular system, yeah, I completely agree. There are, of course, challenges of working at high temperatures, like corrosion and materials related, but yeah, I fully agree with what you said.
There are some other aspects point to be discussed. Is enough? Okay. If
that's the starting point.
I thank those. Yes, it's the starting point, of course. So let's thank all the presenters and panelists. Martin for accepting our invitation. Just to few words that we are half of the project. So the BLAZETEC project will finish in December 2027. So we are a lot of experiments, a lot of aspects to be developed in the next month. So I hope to meet again, Martin, with our solution in a very good stage of development. So
that would be great, Alejandro. I will have an eye on it. As I said, we're having a broad look on those technologies because we believe that there's a strong future. And as we build our system, and you have seen it, we built our storage material on modularity, the full system on modularity, so it can be easily adjusted to new technologies. That's what we had in mind building that setup. So curious about the outcomes.
Thanks. Also, in our case, we are very curious to understand if the idea is good or not. Just I just added the website of the project to have news about the next steps, and thanks also to the European community for the funding. So thank you again to the audience, to the panelists, and to the speakers. And I think we can conclude the streaming, and thanks to all again.
Yep. Thank you.
Thank you.
Bye.
Thank you.
Important next steps.
Thank you.
Yeah.
Bye.
Thank you.